OK， 就是我们有有一个小考，第一个小考在今天的10点半左右开始。If you have a friend, OK, in this class and you don't see him here, OK, and you want to, show your friendship to him, OK, for her, OK, it's about time to remind your friend, OK. 如果说你有一个同学，你知道他修这堂课，然后你现在没有看到他，那你如果说你觉得他是算作你的朋友的话，你可以提醒他一下，今天会有小考。So， 可以吗 ？So let's get started, okay? So last time we finished till here, right? So basically, we are able to show you, okay? For example, okay, this is the original matrix, okay? After the elementary law operation becomes something like this, and the corresponding, elementary matrix would be, for example, from here to here, okay, you exchange the first row and the second row. So you can see that, where is it? Here. Okay, this indicates the operation that you have here. So multiply this one with this one, you get that. Okay, same thing, okay, from here, okay, you multiply -2 to the first row and add to the third row. So that's equivalent to multiply this matrix to this one, and you get this one, and so on. So basically, like the second row here indicates like the corresponding matrix, okay, that you need to multiply in sequence in order to get to this final like identity matrix. Okay. So in other words, okay. Okay, putting this one, okay, the original matrix here, you multiply this one, this one, this one, this one, okay, this one, okay, in sequence, you get the identity matrix. So that's where you put them, right? In this sequence, okay, be careful, in this sequence. So in other words, because this is A, right? So you A multiply something, you get an identity matrix. So this something is actually A inverse, right? It's actually A inverse. And if you want to get, if this one represents A inverse, the inverse of the inverse is A itself, right? So you try to inverse this one, you get A as well. So how do you get inverse? So basically, because this is a multiple matrix. So you get like an inverse of everything, and you put them in the opposite order. Okay, so for example, for this one, it's inverse matrix is this one. For this one, it's inverse matrix is this one, and so on. Okay. So well, that's pretty much about it. So actually, of course, we say theoretically, okay, you can get A from the inverse of this matrix, okay. If you want to verify that, okay, verify if this is the case, you can just multiply them and just verify if the multiplication of these matrices, okay, result in A or not. 所以你看这乘出来的是一个 A。So I think we end here, okay, last week, okay, and then we are about to talk about this equivalent condition, okay, but yeah, I think we ran out of time, okay. So okay, here is the thing, okay. If A is an n times n matrix, then the following statements are equivalent. First, A is invertible. Okay, what do we mean by invertible? It means there's A inverse exists, right? such that A inverse times A equal to A times A inverse equal to identity matrix, right? Okay. So keep that in mind. Keep that in mind. Okay. So first we know A is invertible. So can we obtain the second one from the first one? Okay. So AX equal to B has a unique solution for every n times 1 column matrix B. Okay? Well, if that's the case, okay, if that's the case, first, okay, the first one, we indicate A inverse exists. Or another, according to the definition, okay, A inverse times A equal to A times A inverse equal to identity matrix. So if you want to get the second one. Okay, because A inverse exists, so you just, A inverse times A times B, X. Equal to A inverse times B, right? Basically, we multiply A inverse on both sides. Okay, so this one will get us X equal to A inverse times B. So this one is, this is an indication that a unique solution exists for this, system of linear equation, right? So from 1 to 2, that's easy. How about from 2 to 1? If AX equal to B has a unique solution for every n times 1 column matrix B, can we get like A is invertible? Okay. If this is an A, and your X equal to B, okay, then we know okay, we can, how do we solve the linear equation, system linear equation? Gaussian-Jordan elimination, right? That's normally what we know about, right? So basically, it's just, for example, like multiply, blah, 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 something like eventually, okay, convert it into identity matrix times X, okay, equal to, something here, right? Right? I mean, the intermediate process, okay, each step is elementary row operation, right? So this is basically like what we do for the Gaussian-Jordan elimination, right? Right. So each of these elementary row operations, as I said, basically it indicates something. You multiply EI on the left-hand side, right? Right? Okay. Previously, I already told you that. So from the previous discussion. So basically, okay, the whole thing can be considered. The whole thing can be considered. You multiply, for example, E1, E2, En, okay, times your A, then times X, equal to the same thing, okay, En, E1, times D. Okay, each of them is a corresponding matrix for the elementary law operation. Okay, and this one will result in I, right? This one will result in, well, just this thing. Okay? Right? So that's like how we get the job done, okay, when we solve the system of linear equation, right? It's just like previously, in our previous discussion, before we discuss this, you probably don't know this is like a series of matrix multiplication. But now, with the discussion of last week, okay, each elementary law operation is equivalent to multiply corresponding matrix on both sides. Okay, so basically, okay, this means what? This means well, A is invertible, right? Because this thing is basically the inverse of A, right? Right? This is the inverse of A. Okay, so you can, from here you can, go back from 2 to 1. Okay? So far so good, right? So 1 and 2 are equivalent. We have others to discuss. Okay? So if you allow me, I will erase this. Is that okay? Okay. So now, okay. From the second one to the third one, it's a very, very trivial, right? Because the second one say okay, AX equal to B has a unique solution for every n times 1 column matrix B. And then, okay, I say AX equal to O is it has only the trivial solution. So AX equal to O, by the way, AX equal to O is what we call so if the right-hand side is always just like a bunch of zeros, right? Okay. The opposite hybrid. Suddenly forgot, but that's fine. Anyway, AX equal to O has only the when we say has only the trivial solution. The trivial solution means that x1 equal to 0, x2 equal to 0, blah 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 blah. All the xi's are 0. Obviously, putting xi's to be 0, you have AX equal to 0, O for sure, right? So we say, okay, so from the second one to the third one, okay, it's obvious. Why? Because you can just make B to be O, then you can, from 2 you can get 3 directly, right? Okay, from 2 you can get 3 directly because you can just make B to be O, okay. That's trivial. So from 2 to 3, that's trivial. Okay, 2 to 3. That's just that. B to B. How about from 3 to 2? Actually, we don't have to make 3 to 2. We can just add 1 to 2, 2 to 3, 3 to 4, and 4 to 1, 2, 3, 4, 5. 5. And then 5 back to 1. Okay, so I've done that. Okay, from 2 to 3, I've done that, right? From 3 to 4, let's have a look. From 3 to 4. Okay. A is row equivalent to IN. Okay. Again, okay, if AX equal to 0 has a trivial solution. That means like after the the Gaussian-Jordan elimination, what you have is IX equal to 0, right? Right? If this is not the case, you are going to end up with a lot of solutions, right? 对不对？就是你经过高斯乔登那个消去法，你最后面应该是就是 x one， 就是等于说只有 x one， 就是这边就是这样子，这样其他是，对不对？根据高选 Jordan elimination 的那个 property，if this is not the case, if this is not the case, okay, according to Gaussian Jordan elimination, I mean, you may have like some the bottom row to be all 0. That's also possible. Okay, some row may be 0. But if that's the case, then you are going to end up with not only the trivial solution, but a bunch of solutions, right? I mean, 就是如果说你那个写出来，比如说我现在随便讲说，假设3个好了，就是说 x1 等于什么东西等于0，那 x2 等于0，然后假设有3个好了 ，x3 那一行没有 ，x3 那一行没有，那代表说 x1、x2 等于0，那 x3 可以是任何的值，对不对 ？x3 can be anything, right? So you have like a lot of solutions. So the solution will not be unique. So the only case the solution is unique is that after the Gaussian-Jordan elimination, this part is identity matrix. So x1, x2, then x3 is 0. So we have like all of that matrix. This is of course a 3 times 3 case. Okay. 假设是3乘3的话，如果你少掉一个，那你就会无限多解，对不对？所以一定是这样子，这样子，这样子，对不对？那既然是这样，你写成矩阵的形式，这边就是 I 乘上 x， 对不对？就是 I 乘上 x， 对不对 ？Okay, so from 3 to 4 has done. Okay, we are done with 3 to 4. Because okay, all these elementary row operation, as I said earlier, okay, can be indicated by E1, E2, En. Okay, and you just basically what we are doing is AX equal to E1, E2, and the left, right hand side is also this bunch of E1, E1, but because they modify to 0, so this one will be 0. Okay, but because we have this. Okay. So so from 3 to 4, A is going equivalent to IN. Okay. So the last from 4 to 5. Okay, 4 to 5. If A is no equivalent to IN, A can be written as a product of elementary matrix. Okay, and So if A is row equivalent to IN, okay, from 4 to 5. Okay, so A is row equivalent to IN. That means what? That means, okay, there exists, okay, a bunch of, so A can be, go through like this, Gaussian Jordan inversion, you can get an identity matrix, and each of these steps is elementary row operation. That's what we call row. A is row equivalent to IN, right? And then this is E1, E2, En. So in other words, okay, E1, E2, En times A equal to I. This is what we know, right?对不对？我们知道这个，对不对？对，如果说是 A is row equivalent to IN， 没有这个东西 ，we have this. Each of these is the corresponding matrix for the row the elementary row operations that you need to convert A to I. Okay? So in other words, okay, as I said, this part is, you can consider this part as A inverse, right? Okay, but we know that the inverse of A inverse is A itself, right? So we know like so A inverse, another inverse. This is A, right? We know this, right? 对不对？你把它反过来再反一次，就回到自己。OK， 所以这个 this one OK， so you just like E N E2 E1 the inverse. And then according to what we know, this is like E1 inverse, E2 inverse, En inverse, right? Right? And we know like for each of these elementary matrix, okay, its inverse is also elementary matrix, right? 我们就只有3种 elementary matrix， 一个是什么？两个互换，对不对？就是譬如说，第一个跟第三个如果互换嘛，那就变0、0、1、0、1、0、对不对？你把第一个跟第三个互换，它的 inverse 就是再互换一次就回来，对不对 ？OK， so it's the same thing. OK, its inverse is itself, right? 那你把一个 row 乘上一个 constant， 那你把这个 row 乘上 constant 的导数就回来了，对不对？对不对？所以 inverse 这个 elementary matrix 都是可以都是 invertible， 而且它的 invertible 它的 inverse 也是 elementary matrix。OK， so each of that is elementary matrix。那第三个就是你把某一列乘上一个数字加到另外一列，对不对？那你就把那一列乘上那个数字的相反，就是比如说原来乘2加第三列好了，那就把那个列乘上负2加回第三列，就把它消掉，对不对？对，那这还是一个 elementary row operation, right? So each of that is elementary row operation. So in other words, A can be written as a multiple of elementary matrices. That's exactly what I showed you. These are elementary matrices. Okay? OK 吗？讲到这边 OK 啊，好。And the next one, okay, from 5 to 1. Okay, I forgot. This is a cycle. So from 5, I will have to go back to 1. If A can be written as a product elementary matrices, okay, then we say A is invertible. Okay. So if A is something like this, if A is this, so from 5 to 1. If A is E1, okay, and we say A is inverted. Why? Because A inverse will be this thing inverse, right? It will be En inverse, like En minus 1 inverse, E2 inverse, E1 inverse. But we know elementary matrices, all the elementary matrices are invertible. Okay? So all this exists. All this exists. And you multiply them up, of course, we still have something, right? So that's a very simple fact. So if A can be written as a product of elementary matrices, A is invertible. Okay? So that's it. So we done 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to back to 1. So they are all equivalent. Okay? And then it's the next one is an interesting thing. Okay? To be honest, it's not that useful, but you will find that sometimes this decomposition come in very handy in certain applications. Not necessarily useful. I mean, in the sense, I mean, when they are introduced in application, we talk about application, how they are introduced. Okay. So we say the matrix. Okay, here, that's what LU factorization or decomposition. Okay. The matrix is called, lower or upper. Okay, so let's say lower triangle. If all the entries above the main diagonal are 0. So the lower triangle just means something like this. You have something. So you have something here, but all the elements above the diagonal are 0. Okay, that's lower triangle. So if it's upper triangle, then we have it's opposite. So we have something here, but everything below the diagonal are 0. Okay, so so if A can be written as like a lower triangle multiplied, to upper triangle, okay, we call that the LU factorization or LU decomposition of A. Okay， 所以说 A 可以被写成说是 LU 啦 ，L 乘上 U，L 代表是一个下三角的矩阵，那 U 代表是一个上三角矩阵。OK， 那我们就说这是一个就是 A 的这个 LU factorization 或 LU decomposition。那这边给了一个例子啊 ，Here we have an example. So this is A equal to this one times this one, and this one is a lower triangle, right? Because like the upper, all the elements above the diagonal are 0. Okay, so this is a lower triangle, and this one is upper triangle because everything below the diagonal are 0. You can verify if this A I mean, you know, is the result of this multiplication. 你可以自己检查一下。Okay. So here, okay, we are trying to give a ratio why we want to do it. But to be very honest with you, nobody will solve like a system linear equation by using the LU decomposition. Okay. But anyway, I mean let's stop anyway. Okay. So if A can be written as a LU, I mean L times U, okay, then AX equal to B will be L times U times X, right? Equal to B, right? Obvious, right? So you can, because like you can have UX equal to Y. You can have UX equal to Y, and then this equation becomes LY equal to B, right? LY equal to B, right? Remember, L is a lower triangle, right? Lower triangle. So let me show you, okay? For lower triangle, something like this one. This is a lower triangle, right? So this one time multiply x equal to b, then it's very easy to solve, right? Because you can start from the top one. Okay, this one is 1, right? So you know what is x1, and then you mark. If this is non-zero, then you just you put whatever x1 you have from the first row, and you can solve this for the x2, right? And if you know x1, x2, you can do x3 easily, right? So, I mean, for lower triangle, I mean, it's solving lower triangle is very easy, okay? And once you have the, well, actually it's not x1, x2, x3, it's 1, 1, y2, y3. So, 1, 1, y2, y3. Okay, because you are doing this, okay? And once you get 1, 1, y2, y3, plug in 1, 1, y2, y3 here. And again, it's a ux equal to 1, y2, y3, right? And then the upper triangle can be solved also easily. It's a back substitution. You get like x3 first, and then x2, and then x1. Okay? But nobody will be stupid to do this way, okay? Why? 没有人会这样子解方程式的啦。为什么？你要先去把你的那个 A 先做 LU 那个 factorization， 然后再去做这些东西。你做这个 factorization 的困难度已经差不多跟解这个方程式一样了，那你干嘛？花时间？对。但是我这样讲，并不是说 LU factorization 没有用，它在别的地方有用。It has other applications. Okay, that's more important. There are some important property that makes this decomposition, this factorization very useful. For example, okay, if the matrix is either lower triangle or upper triangle, it will make the computation of determinant. 就是那个它的那个determinant 中文行列式，对，行列式就是 matrix 的行列式。如果说是 upper triangle 或者 lower triangle， 它的行列式就是它的对角线相乘就结束。Okay, so it's there are other important applications, okay, for LU factorization, but for now, okay, we just use this as a motivation. But this motivation obviously is stupid. Nobody do solve the system really this way. But anyway, we still need to know how to get the job done, right? How do we do this factorization? Okay. So we want the product of lower triangle matrices. Okay. Sorry, we want the lower triangle matrix. Okay, but we know like if A is a lower triangle matrix, okay, if A and B are lower triangle matrices, the product of them will still be lower triangle. Okay, this is okay. I will not prove this, but I will let you think about this. How to prove it? Okay. Now, if A and B are lower triangle, the multiplication will still be lower triangle. 如果 A 跟 B 是下三角，它们乘出来还是下三角。Okay, so this is another interesting property of lower triangle. I mean, the similar property can be said for upper triangle. Okay, 如果你有两个上三角形的矩阵，相乘了以后它还是上三角形。Okay, you can verify this by yourself. It's very interesting property. Okay, so having this fact, once we understand this, if we can write it A times E1 into blah blah to E can equal to U, okay, and the E1 into blah blah, they are all lower triangles. Then their multiplication will be a lower triangle, right? 对不对？如果我们可以写一下 equal to U， 那这个是什么东西？其实你如果看这个 ，if you take a look at this， 这就是高轩 elimination 的结果嘛，对不对？这个高斯消去法，你会得到一个 upper triangle， 对不对？记不记得高斯消去法怎么解那个方程式？你就是用那个 basic row operations。elementary row operations， 要做到最后变成一个矩阵变成一个 upper triangle， 然后用 back substitution 去解它嘛，不是吗？是吧？对不对？大家还记得哦，希望大家还记得。So， 那我们能不能确认说，我们每一个这个 elementary row operation 的那个，就是它的那个矩阵是 upper triangle？我问同学哦，我们做高斯消去法的时候，那个高斯消去法，我不是讲高斯纠人 elimination，OK， 我讲高轩 elimination，OK， 因为高轩纠人 elimination 到最后你算到这边了以后，你还要从这边把这个最后往上消，对不对？就往上消，对不对？所以你必须要那个从后面的往上去弄，对不对？但是如果说你在做高斯消去法的时候，就是这个。变成一，然后把下面消掉，这个变成一，下面消掉，都是往下，对不对 ？All the elementary row operation involved in Gaussian elimination are doing, you are doing, what should I say that? You are working toward like the lower rows, right? You are working toward the lower rows. Okay, so their corresponding matrix， 如果说是某一列乘上一个数字，这个当然是它的 corresponding elementary matrix 是 upper triangle， 对不对？对不对？那另外一个对不起，是 lower triangle。那如果说你是把某一列乘上一个数字加到下面的列，这也是 lower triangle， 对不对？对不对？这也是一个 lower triangle matrix。OK， 什么东西？唯一一个东西，它不是那个 lower triangle。你看一下这个，我们到这边，就是从第一步到这个开始到这一步，再到这边就是我们的 upper triangle， 对不对？对，到这边就停下来。好，我们现在看一下。它的相对应的，这是 lower triangle， 这没问题，对不对？那我们把这个乘上0.2，就算把这个也算上去，这还因为你这边还是一个 lower triangle，upper triangle， 所以你既然把这一步也算上去，你这个乘上就2分，这个第三列乘上就2分之一，这也可以当做 upper triangle， 对不对？那只有哪一步不是 upper triangle？ 第一步啊。第一步不是 upper triangle， 因为你有一个 e 在 ，you have this one is not upper triangle, right? 如果两列互换，它也不是 lower triangle， 也不是 upper triangle， 对不对？如果两列互换，所以重点是什么？重点是说，如果你的高斯消去没有两列互换的这个问题，那你保证你会得到一个 LU factorization。OK， 因为你这些相对应的这些乘上去，这两个 lower triangle 乘上去还是 lower triangle， 对不对？对，所以说，所以。所以if EK E2 E1 times A equal to upper triangle, and all these elementary matrices are only adding and multiplication by scalar. Okay, so you can see these two operations. We do not include like exchanging two rows here. Right， 我们没有包含那个交换两个 row， 就是这边讨论的 row 那个 elementary row operation 只有两种形式，一个是什么？一个是某一列乘上一个数字，或者某一列乘上数字加到下面的列。OK， 那如果是这样子 ，then A equal to blah 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 times U, and this like the inverse of that are still upper triangle. And this is lower triangle. They are all lower triangle. So multiplication of that is a lower triangle matrix. Okay. So for example, okay, now you are given a matrix A like this. We want to find the LU factorization. It's LU factorization. I want to emphasize that this LU factorization is not necessarily unique. 就像说你两个数字相乘嘛，比如说你说没有12可以写成两个数字相乘，我问你说，那你给我它的这个乘积，你当然可以是2乘6，你可以什么3乘4，对不对？所以哪一个是错的？两个都对，对不对 ？OK， 所以 LU decomposition factorization。The solution 有可能不为一哦，有可能不为一。OK， 我要先让你们知道。OK， so anyway， OK， so for this one， well actually because I'm too lazy, you can verify yourself, but this one by using like this Gaussian unification, okay, to find the LU decomposition, but it's going to be something similar to this one because this is what we had here, right? This is A, this is L, this is U. But how to get this L and this U? Okay, you have to practice it. Okay, so I think okay, let's practice. Okay. So from here. So if you want to eliminate this one, we have already done that before. So you multiply -2 and add to the third row. So you will get then this is 0. Multiply -2, so it's 6. Okay, 6 plus -10 is -4. So this one is 2. Okay, and then okay, this one, the second row multiply 4, add to the third one. 1, negative 3, negative 4, 0, 1, and then multiply 4, add the so it's going to be 0, 4, 4, 3, 14. Right? Okay, so the corresponding elementary matrix, okay, this one is what? You multiply negative 2. Okay, so negative 2. So it's this one, right? Because this is already upper triangle, right? This is already upper triangle. If you want, you can multiply the third row by 1/14. Okay, but you don't have to. Okay, this is good enough. So this one, okay, from here to here, you multiply this one to this one, you get this. Okay, what else? Okay, from here to here, you multiply 4 to the second row, add to the third row. 1, 0, 0, 0, 1, 0, 0, 4, 1. Okay? Right? So in other words, this one, let me write A here, okay? I'm too lazy, okay? A times, let's call this one E1. Let's call this one E2, okay? So E1 times E0. So E2 times E1 times E2 equal to this, let me call this one outer triangle. Outer triangle. Right? And then if you want, we need to modify A equal to, okay, so you multiply negative, the inverse of E2, inverse of E1, and then this one, right? Right? And what is the inverse of E2? Inverse of E2. Inverse of E2 will be, just 1, 0, 0, 0, 1, 0, 0, negative 4, 1, right? So it is still a lower triangle, right? The inverse of E1 is like 1, 0, 0, 0, 1, 0, and 2, 0, 0, 2, 0, 1, sorry. So this is the inverse of E1. So this, again, this is a lower triangle, right? So you multiply the lower triangle with the lower triangle, so this one is a lower triangle. Okay? Is this like the same as, yeah, it's the same as what we have here. So these two, we multiply this E negative 1 to this E2 negative 1, you should get this. We can give it a try. Okay? We can give it a shot. Okay? So with that, okay, now we know like this one can be written as this one times this one. This is lower triangle, this is outer triangle. Okay? And if you have that, okay, then we first let, remember, with that, because like, we have this L times U times X equal to B, right? So with that, this one to be Y first. Okay, so now we have L times Y equal to B. So we try to solve this. So, so this is so this one. So we write that this lower triangle times Y equal to this one. Okay. Then we, by using the 4 substitution, we get y1, y2, y3 to be this one. And with that, because y is ux equal to y, right? So ux, so we will again solve like this is u, okay, times x equal to this one, y. And then we use the backward substitution, we get the result to be this. But are you going to be this stupid to use this way to solve like a system of linear equation? 你会真的笨到说用这个方法来解吗？我当然 in exam if I ask you, okay, that you have to follow this, then you, of course you do this way, okay? 因为在考试我就是要你这样做，你当然就是这样做。但是如果说你是，因为你在写这个，你在做这个 LU 考试的时候，其实呢。就旁边带着，你旁边带着你的那个你的 B 就好了，对不对？你就直接解到，当你解到得到你的那个，因为你在得这个，你在算这个 LU factorization 的时候，事实上你在做高斯消去，所以你当然你用带着 B， 你高消去法得到你的那个 upper triangle 的时候，你事实上已经可以用 backward substitution 把它解出来。所以没有人会真的去用 LU decomposition 来解线性倒顺序，因为这样做太绕了，对不对？不是说它不能做，而是说我觉得这个是一个很笨的做法。但是重点是在说，如果给你一个 matrix，if I give you a matrix, I want you to do LU decomposition. You need to know how to do it. Okay. Let me put it this way. The application, the more meaningful application will come in at a later time. OK， 比较有意义的这个使用的方法，在后面才会真的出来。举个例子，像深度学习里面也有一些东西，其实可以去用这个东西。这个我就不细讲。OK， 如果说你去做深度学习，所以说就是那种深度学习研究的时候，可能会用到。OK， 好吧，那 anyway， 那我们讲到这里。Then OK， here we are trying to discuss some applications of like system of linear equations. Okay, the first one is the stochastic procedure. 下课时间到，我们先休息10分钟，好不好？那回来我们再继续讨论，把这一章上完，然后希望都讲一点下一章。